How is everyone? Good, good, good. Nice to see everyone is now booked for a slot. Happy to see. The Monday slot all came and went. Everything's been going well so far. There's more obviously today and Friday, so that's good. And it looks like everyone found a time that works for them. If that's not the case, if you're canceling something you need to be in otherwise because of your slot, let me know. We can pick other times outside of the ones that I posted. I just posted those ones because I figured it'd be nice to keep them all together, but we can certainly make exceptions. It's not a huge class, so it's not like we have too big of an issue there. I'm going to switch over to this. We have been talking about electrochemistry and started out talking about redox reactions, assigning oxidation numbers, and then we moved kind of to electrochemical cells, which means taking those redox reactions and separating them physically into two different areas and having the electron transfer part of the redox reaction take place through a wire. You know, the electrons get transferred through the wire and then move the other half reaction through the electrode. We looked at all the different kinds of electrodes. We said there are electrodes that are metals that actually participate in the reaction. Either metals get deposited onto the electrode or the electrode dissolves away. We looked at inert metal electrodes like platinum wires, where you have a redox reaction between two species that are both in solution, like maybe iron 2+ and iron 3+. And we also looked at electrodes that involved a gas. So the basic setup for an electrochemical cell might look something like this, where you have one container, let's call it a beaker, right? We could make a beaker if we want. And we have a second one over here. And what we need to have in each of these solutions is some sort of electrode. So for the Daniell cell had an electrode on each side. You know, you could have zinc maybe as a material for one side, copper is the other. And in these cases, both of these are solids, obviously, like they're rods of metal. And they are immersed in a solution that contains the ions of that particular metal. So on the zinc side, we have zinc 2+ in solution. There's got to be some counter ion in there as well. You can't just have zinc 2+ and no counter ion. So I don't know what counter ion is, maybe like nitrate. And for every zinc 2+, there's 2 nitrates, obviously, because you need to balance the charge. On the right-hand side, the ion in solution would be copper 2+. And again, some counter ion that's in there as well. So the two half reactions here would be maybe like a zinc solid goes to zinc 2+ plus 2 electrons. So this would be a reaction, a half reaction, where the zinc solid is dissolving away. The electrons are disappearing from that half reaction. And where they go is the other side, right? They go over to the copper side. And to get them over there, you need to connect them by a wire. So the electrons head along that way that are produced in this reaction, and they're picked up on the other side. They go into the electrode, and then the ions, this copper 2+ ions, when they contact the electrode, when they collide with it, they can pick up those electrons and become copper 0. So that would look like this, Cu 2+. It would need 2 electrons, goes to copper solid. And these ions that we have here and here are in the aqueous state, right? So we would say that Cu 2+ Aq, because they're dissolved in water. The electrons, I guess we don't even give a state because they're not really dissolved. They're not really solids, liquids, or gases. So we just leave them like 2 electrons. So if you add those two half reactions together, the electrons will cancel. They have to, because the electrons for one half reaction come from the electrons from the other half reaction. So our overall reaction would just be like Zn solid plus Cu2 plus Aq goes to Zn2 plus Aq plus Cu solid. Right, so it would look like this. By the way, I should ask, is anyone colorblind? Some people have a really difficult time seeing red when it's on a screen. I know Dr. Banks has that issue. So if you're like using like a red laser pointer, he has a really difficult time following the laser pointer because the red is, he just doesn't register well. So yeah, maybe I should be switching to blue or black or something like that. Nevertheless, this is an electrochemical cell that is missing one piece. Does anyone see the piece that's missing from this electrochemical cell? Salt bridge, that's right. Because what's going to happen if you start pumping electrons to the right side of this reaction, very quickly you're going to build up negative charge on the right side, positive charge on the left side, and that's going to create a potential that works in the opposite direction. Electrons are going to have a harder time moving to the right-hand side if there's a huge positive buildup of charge on the left. So that what would happen is this would start, maybe you get a little bit of reaction, then it would just stop when you started to build up that charge. So to prevent that charge buildup on one side or the other and allow this reaction to proceed smoothly, we need a salt bridge to allow ions to travel left and right so that the charge remains balanced on each of these half reactions. So, you know, you can put it in like this. It's basically like we call these U-tubes. They often contain like a gel-like material that is salty. And we have some sort of inert salt that's in there, like, I don't know, potassium nitrate, right? Nitrate and potassium are not going to participate in a half reaction in either side. So as electrons get pumped to the right, potassiums get pumped to the right too, to keep the charge balanced. And as the potassium gets pumped to the right, the nitrates get pumped to the left to replace the negative charge that is lost when the electron goes. So you have these ions move through this salt bridge. And I think we looked at an example with a very crude salt bridge that was just like a wet paper towel or like a wet piece of paper. And ions can travel as long as it's wet. Ions can travel through that medium as well. Although it's not going to be a very rugged electrochemical cell. It might work for a few minutes, but it'll dry out easy and then not be too good. Okay, when we have an electrochemical cell that looks like this, we have a method of drawing a shorthand version. So we can write out what this cell actually is without having to draw all these beakers, a salt bridge, all that kind of stuff every time. So the shorthand version looks kind of like this. You start at the very, so we write this out left to right, okay, like you would write out anything you're writing. And it starts with the side where the electrons are being lost from. So you can kind of think of this as going left to right. It's the journey of the electrons. What direction are they going? So if something loses an electron, we call that oxidation. The electrode where oxidation takes place is called the anode. So we would call this side here the anode, and this side becomes the cathode. Cathode is the side where the reduction takes place, where the electrons are traveling to. And so we start to write out this shorthand version starting at the anode side. And the way we do this is we just write the material that the anode is made from. So we know it's made from zinc solid, right? That's the anode side. Then what we do is we use a vertical line every time there's a phase change, okay? Every time we move to a new phase. So the zinc solid is in contact with zinc 2 plus ions, but they're in different phases, obviously. One's solid and one's aqueous. So what we would do is use a vertical line, and then we would write zinc 2 plus aqueous. So that's the complete left side of this particular reaction. When you have a salt bridge, the salt bridge separates the two half reactions physically, right? Well, it connects them, but it's the barrier, it's the physical separation between them. We use a vertical double line. So that looks like this. That means salt bridge. So that's the separation between the two half reactions. Then what we do is we kind of we treat the right-hand side of this equation the exact same way, except we kind of do it in reverse. So the outer two things that you always write are the two electrode materials. Okay, we move inwards, and then the salt bridge is in the center. So that means the next thing we come across here is the copper 2 plus AQ, vertical line, copper solid. Okay, so the outermost things you see are the electrodes. We have the anode here, and we have the electrons travel from left to right. Cathode over here. Okay. Let's look at another example. Okay, let's look at another electrochemical cell. The liquid in there. We have this inverted salt bridge, this inverted U tube over here. And in this side, we're going to use there, it looks like a fly swatter. Okay, but it's not. This is platinum metal. And the redox reaction going on here is going to be between iron 2 plus and iron 3 plus in solution. And we can leave the right side the same. Let's go to copper 2 plus and a piece of copper solid. And we're going to connect these by a wire, set up this electrochemical cell, and see what happens. So what we would do is on the left-hand side is we would start with the electrode material, platinum solid, phase change, vertical line. Next, we have in solution both iron 2 plus and iron 3 plus in solution. They're in the same phase. So we don't use vertical lines to separate them. What we use is a comma to separate them. And we put the one that is most reduced closest to the electrode. So the one that's most reduced is iron 2 plus. So we would write this, iron 2 plus, aqueous, comma, iron 3 plus, aqueous. Next, we got the salt bridge, double vertical. And then the right side is the same as before. Cu2 plus, aqueous, copper solid. Okay. We can do one more example before I go back to the slides. And this is going to be using one of our gas electrodes. So let's draw another electrochemical cell. Inverted U-tube in there. And in this case, we're going to have one of these fancy, so the center piece here is platinum. And we have this thing that's kind of coated in glass. And we have like an opening here and here. And in solution, we have H plus. It's an acidic solution. And here we have hydrogen gas that is pumped in there, and it can bubble out of these holes. So this was our hydrogen electrode. In fact, we have a name for it, SHE, standard hydrogen electrode. That's what's on the left-hand side here. We have our salt bridge. And over here, pick another half reaction. So we can use, I don't know, piece of metal, pick something simple here. Pick a new metal if you like. We can use, I don't want to use a metal where there's multiple oxidation states. I'm just going to use the zinc one again, or copper. Why not? Let's leave this simple. And then these get connected by the wire. So if we're writing this one out, we again start on the left-hand side, and we use the material that the electrode is made from, which is platinum. And this is an inert electrode. It doesn't participate in the reaction, except it provides surface area and a conductive material for electrons to move back and forth. But there's nothing that gets deposited on the electrode, and the electrode itself doesn't react away as the reaction proceeds. Now we have a phase change, and we have two different species reacting at this electrode that are in two different phases. One is hydrogen, which is a gas, and the other is H+, which is aqueous. We separate them both by vertical lines, and again, the convention is to put the most reduced thing closest to the electrode. Or in this case, in fact, I think in every case, it's the gas that's going to be closest to the electrode. Vertical line, H2 gas, vertical line, H plus AQ, and we use vertical lines because they're different phases, whereas up here, remember, we just used a comma because they're in the same phase. Okay, then we use a double vertical line for the salt bridge, and then the right side is the same as always. And that is our abbreviated L notation. So now, as experienced electrochemists, you could look at this abbreviation and draw me a picture of what the electrochemical cell might look like. Cool. So obviously you can see why this was adopted. It's a lot cleaner, takes up a lot less space. And as an experienced electrochemist, you could read that and get all the same information that you would get from up there. Now, one other thing that I wanted to mention is sometimes we see electrochemical cells where you have the same reaction going on in the left side and the right side. We'll talk about this a little bit later. They're called concentration cells, where the two half reactions are exactly the same. So for example, you might have, zinc and zinc 2 plus. Zinc like this. You might look at that and say, well, how would that work? There's the same reaction on both sides. There's no driving force for the electrons to move. Well, in situations like this, the driving force might be, the zinc 2 plus might be 1.0 molar, and over here, it might be 0.2 molar. Then the driving force is, for this to come to equilibrium, is to have the concentration of zinc the same on both sides. In that case, there would be a driving force for electrons to move to the left until the concentration was the same on both sides, and we would say it's 0.6 molar and 0.6 molar. And once those concentrations are the same on both sides, we would say that the reaction has come to equilibrium. And another way of saying that, the standard way we would say that for an electrochemical cell, is that the battery is now dead. So a dead battery is just when the cell reaction has reached equilibrium. Cool. Now, I have here next couple of slides, I think, are all just exact repetition of what I just told you. This is explaining the cell notation. This is explaining one where you have multiple ions in solution, the iron 2 plus, iron 3 plus. This is the case where you have the hydrogen electrode, the SHE. Okay. And here we have an example. So I'm going to move past this because I feel like we've covered this aspect quite well. We've drawn several electrochemical cells. We've labeled all the things, and the line notation I think we're okay with. Perfect. Do you want to do one more example of this? They almost stick their neck out. We can. These aren't too bad. Well, let's do one. Why not? We'll do it quick. We want to write equations for each half reaction as well as the overall reaction. So you can see on the left we have copper solid. This is the anode. This is where oxidation is happening. So the oxidation means it's losing electrons. So the reaction here would be copper solid goes to copper 2 plus AQ plus 2 electrons. The other side is the cathode, where reduction is taking place. So reduction there means it's gaining electrons. So that would be going from Cl2 gas to Cl minus. That would look like Cl2 gas plus an electron goes to Cl minus. Now that's obviously not balanced. Cl2 will make 2 chlorides, and to make 2 chlorides, we need 2 electrons. Okay. Now, if we want to write the overall reaction, we just add these two together. In order to add them, you need to have the same number of electrons on each side, which we do. So this just becomes Cu solid plus Cl2 gas goes to Cu2 plus AQ plus 2 Cl minus AQ. Cool. Everyone's happy? Wonderful. And we're all happy. There is another one here on the slides. I'm not going to go through this one, but if you want to practice one, see what it's like. Generally speaking, when there's questions like this that are in the slides, if you look in the notes part of the slides that are all posted, the solution is in there. So you can try it out yourself. We're going to move back to this idea of voltage. So what we want to do with these cells is, of course, there's got to be what we call a potential difference between the two half reactions. There's got to be a driving force for electrons to move one way or the other, or else you don't have an electrochemical cell at all, right? If you just made an electrochemical cell, just put water in both sides, and there's no reaction to have happen, you won't get a voltage. Now, we looked at a number of different kinds of electrodes, a number of specific half reactions that could be used to do one half of an electrochemical cell. So we have all kinds of choices what those half reactions are when we want to build one of these cells. And depending on what two reactions you pick, you can get very different voltage values. And if you want a specific voltage for a specific application, it's very important that, of course, you pick the right half reactions and also pick the right concentrations and pressures and so on. So it works out for this Daniel cell, the one with copper and zinc on the two sides. If you put the copper concentration and zinc concentration at exactly 1 molar, 1.00, what we find is that if you hook it up to a voltmeter, it'll tell you the voltage is exactly 1.10 volts. So the question is, could we have predicted that that would have been the voltage in advance? Because there are hundreds of half reactions that we could potentially use to build a cell. Let's say we wanted to have a cell where the voltage was 1.8 volts or 1.3 volts or whatever. Can we tell what the voltage might be before we go ahead and build the cell and measure the voltage, right? And I wouldn't be asking you this question if the answer wasn't yes. So it's impossible to measure a voltage on just a half cell. You always need a complete electrochemical cell. So what you're always measuring is voltage difference, potential difference. You can think of this as like potential energy difference between two sides of a chemical, of the two sides of the two half reactions, basically. So you're always measuring just a difference between two things. It's kind of like delta G, right? When you have a delta G for a reaction, what you're measuring is the difference in potential energy between the products and the reactants. You're not actually measuring G on one side as an absolute value, and then G on the other side as an absolute value and subtracting. You can't do that. We don't know what the actual value of G is. We just know what the difference is. And the same is true with electrochemistry. We don't know exactly or maybe it's not, maybe that's the wrong way to put it. It's not that we don't know exactly, is that there can't exist a voltage for just a half reaction. You always need two, right? So what happened is electrochemists got together and decided, well, let's just pick some electrode to be a standard. And we'll measure all the other half reactions against this single standard electrode. And then we can come up with a table, we can come up with a list of cell potentials when one half of the cell is this standard electrode, and then the other one is the one that you're measuring. So you could do that, put the zinc one in, put the copper one in, put whatever other one you want in. And the electrode they picked to do this is the standard hydrogen electrode, which might seem like an odd choice to you because it's much more convoluted than a lot of the other electrodes. Like zinc is simple. You put a bar of zinc in a solution of zinc. For this, you got platinum, you got hydrogen bubbling over it. You need to make sure the pressure is right. You have hydrogen ions in solution. You need to make sure the concentration's right. But they picked that one anyway. And I guess we can measure pressure easily and we can measure pH easily. And the good thing is that this half reaction electrode is sort of right in the middle of all of the reactions that we've seen. It can either donate electrons or gain electrons, and roughly half of other half reactions want to remove. It's spontaneous to remove electrons from this half reaction. The other half, it's spontaneous to donate electrons into this half reaction. So this is called the standard hydrogen electrode. This is the same one that we drew before with the glass and the platinum foil or platinum mesh and the bubbles and so on. So we're going to go ahead and give this a value of 0. We're going to say this is standard. We're going to have an electrode potential of 0. So an electrode potential basically means this is a voltage we're going to say exists only for this half cell. And it's kind of artificial. It's kind of fake because you can't have a voltage with just a half cell. We come up with these things, we call them standard electrode potentials. In fact, we usually call these standard reduction potentials. They're always written as reductions. And this would be the half reaction for the hydrogen electrode. It's written as a reduction. It's written as if electrons are being gained by the species. And we would say that this will have, it's assigned a value of E0 equals 0. Okay, so we picked this one, assigned it arbitrarily, assigned it 0, and then every other half reaction can be made into a cell with this and measured against it. Why do we put a little 0 here, do you think? You've seen those little superscript zeros before. What do those mean? Standard conditions, which for an electrochemical cell, it's the same as everything else. It means all of the concentrations are 1 molar and all of the pressures are 1 bar. So this is only true when the gas pressure you're bubbling in is 1 bar and the hydrogen ion concentration is 1 molar. Okay, so we come up with a potential for just the half cell, which is kind of an oxymoron because you can't have a potential difference with one half reaction. And then you hook that up. Like, look, you take the hydrogen electrode that you have here and you hook it up to a copper half reaction. Or you do it again and you hook it up to a zinc half reaction. And it turns out if you put it into the copper reaction, the spontaneous direction for electrons to move is towards the copper. Okay, that's going from left to right. So that would be the anode on the left, cathode on the right. And what we would notice is this reaction starts, electrons start traveling, and the potential difference between the two sides here would be plus 0.340 volts. So what that means is, well, the E cell, 0.340 volts. If everything is 1 molar and 1 bar, we could say that's E0 cell. And we know that that's got a contribution from the hydrogen half and the copper half. There's a difference between the two sides. So that means if we assign this one an E0 equals 0, which we did in the previous slide, that means we can say that this side has an E0, which is equal to 0.340 volts. So we are able to come up with these half reaction potentials, these standard reduction potentials, by doing it this way, measuring it against the hydrogen electrode. If we do the same thing for zinc, we notice that actually the spontaneous direction for electrons to flow is right to left. We would say that they flow from the negative electrode and they move towards the positive electrode. And the voltage that would read here is negative 0.763. The negative voltage is because the electrons are going backwards, I guess. You could say they're going right to left. And therefore, we could say that the E cell, E0 cell, if everything's 1 molar, is negative 0.763 volts. And we can say that because the E0 on this side is 0, the E0 on the other side is negative 0.763. So we call these standard reduction potentials. It's defined as 0 for the hydrogen. We've measured it to be positive 0.340 for copper, and we've measured it to be negative 0.763 volts for the zinc. And this has been done, I think there's actually a table in Wikipedia, if you look up standard reduction potentials, there's like hundreds of half reactions where this number has been measured. Great, so we call these standard reduction potentials. They're always written as reductions. So for the zinc, that reaction would be zinc 2 plus 2 electrons going to solid zinc. And the standard reduction potential E0 is negative 0.76 volts, which is just the cell potential you would get if you hook this up with a standard hydrogen electrode. Okay. Yeah, so negative means that the spontaneous direction of flow is actually the reverse of what we see here. That the zinc doesn't want to be reduced, it wants to be oxidized in that chemical cell. Great. So yeah, we have tables, like this is one out of a textbook, right? We call these electrochemical series, and look at the E0 values over here. Hydrogen is sort of smack dab in the middle, standard hydrogen electrode, which we've assigned to be 0. All the other ones are either greater or less than that. The ones we've seen already, we've seen the copper one, which is right here, 0.34. We saw the zinc one, which is negative 0.76. If you go all the way up to the top of this list, the highest voltage that's listed is F2 plus 2 electrons goes to 2F minus. Okay, everything's aqueous. Well, I guess F2 is a gas. This would be a reaction that in first semester you would say this should be strongly, I guess, spontaneous, right? Fluorine loves to have electrons. It wants 2 fluorides. The fluorides have full octets. Fluorine is extremely electronegative. It would be a very favorable reaction, right? And there's a strong driving force for that reaction, and that's why it has such a high potential. So something that's high up on this list of standard electrode potentials really wants to gain electrons, okay? And if something gains electrons, it's being reduced, so it's an oxidizing agent. So very strong oxidizing agents are on the left here up towards the top. So F2 is a very strong oxidizer. H2O2, hydrogen peroxide, is also an oxidizer. See, oxygen is here. It's an oxidizer, of course, but not the best. Actually, there's many that are much better than it. And as you go down the list, they less and less want to have electrons. So the very bottom of the list is lithium plus. Lithium plus, you can give it electrons and turn it into lithium solid, but it really doesn't want them. Like, it's on the very far left of the periodic table. It's got a noble gas configuration already. So why would it want to take an extra electron? And the answer is it definitely would not. In fact, if you had lithium solid, it would love to do the opposite reaction and give away its electron. So that reaction that lithium plus electron goes to lithium solid, that would be strongly spontaneous in the reverse direction. So it has a negative value, negative 3.04. So notice the weakest oxidizer, the one that wants the most to not have that extra electron, has a half cell potential of negative 3.04. The extreme opposite one, the fluorine, is positive 2.87 volts. So notice they're about like equidistant almost from the zero. So for that reason, this SHE, this standard hydrogen electrode, is a great choice for the standard because it's sort of smack dab in the middle of the range of voltages that you see for other half reactions. Okay. Good. Great. Same thing. This is just a zoom up version of the same thing. Sometimes these numbers vary slightly, like negative 3.05, negative 3.04. What actually happens with these, it's interesting, is people will measure them as people's instrumentation gets better. They may be remeasured and then republished at a later time with like a slight correction. And depending on where this table, the data came from, when it was put together, what textbook it came from, these numbers might have been modified slightly over time, but not much difference. So these voltages, by the way, are an intensive property. So we have intensive and extensive properties. We talked about this back in the thermochem chapter. We said an intensive property that does not depend on the amount of substance, where extensive does. And I think in the thermochem chapter, we used the example of heat versus temperature. And temperature is an intensive property, right? The temperature of the air in this room versus the temperature of the air in the gym could be the exact same regardless of the size. Same is true for E0. It doesn't matter how big the battery is. It doesn't matter if you have a little tiny thing that you build or great big vat of solution on both sides. The voltage of that electrochemical cell will be the exact same. If you change concentrations, it'll change, and we'll look at how that changes. But just in terms of pure bulk. So when you look at batteries, when you buy them, right, like you can get a AAA, AA, a C, or a D. I don't know if there's a B or just an A, but I've never heard of them. All of these have the same voltage. All of these are using the same reactions with the same concentration. The only difference between these batteries is their size. So basically the D battery is exactly the same as the AAA. It's just it'll last longer. It'll take longer for the reaction to reach equilibrium. So you'd need a D battery in something that would draw a lot of electric current. So I don't know. You don't see the D batteries that often anymore. The 9 volts, if you place batteries together in a series, their voltage add together, right? So you have here, you see there's the plus and the minus, there's the plus and the minus, plus and the minus, and the minus, minus, plus, minus, plus, minus, plus. Basically, if you connected these to each other, you would get 9 volts, but they're each just 1.5. And these square batteries, these 9-volt batteries that you use in smoke detectors, if you like cut one of those open and opened it up, what you'll find is there's like 6 of these just packed together. There's like 6 individual cylindrical batteries packed together into that kind of square. It's like a 3x2 in there. And they're connected in such a way that you have wires that connect them up and down and up and down, so that they're all in series, so the voltage amplifies. So same thing, you could build a giant 9-volt battery with 6 of these Ds, and it would be the same thing. So I guess going back to our electrochemical cell where we have the two beakers of solution, you could wire many of those together. You could make this great big series if you wanted and crank up your voltage in that way. Okay, so yeah, this is just saying too, if you have an electrochemical half reaction and you double it, it doesn't change the E0 value. And sometimes you have to double these or divide them by 2 or whatever when you're adding together half reactions so that the electrons cancel. But when you do that, if you multiply the half reaction by some factor, it doesn't change at all the E0 value for that half reaction, that cell half reaction, that standard reduction potential, which is good. We talked about that already. So here's a question. Which is the strongest reducing agent? So a reducing agent is something that reduces something else. To reduce something else, it needs to give electrons to it. So we have to pick something here that's going to donate electrons. That means it's got to be something here on the right-hand side, because the other ones are all ions already. They have no electrons to donate. It's got to be one of these. This value here is our E0 value. It's basically telling us how badly they want to give away electrons or how badly they want to receive electrons. So what we find out is, the higher the value is, the more positive it is, the more spontaneous it is for it to absorb electrons. The further down the list it is, the more it wants to get rid of those electrons. So cobalt, out of all these on the list, it's the greatest negative E0 value. That means that this reaction as written is the least spontaneous. There's the lowest driving force for the reaction as written, but what we're looking for is the one that's most spontaneous for the reaction written in the reverse direction. We want to do a reduction. We want to give away those electrons, not get them. So the one that's least spontaneous to gain electrons will be the most spontaneous to give those electrons away. Okay, so that's how you can think about a question like this. Yeah. We already said that. We got there. Okay, so this is what all of this is coming to. Why do we have these reduction potentials, standard reduction potentials for half reactions? The reason is if you know the two half reactions you're using to build an electrochemical cell, you can use those two numbers and calculate exactly what the voltage of that cell is going to be. The equation is very simple. The E cell is the E of the cathode minus E of the anode. Right? So you build your electrochemical cell, you look on the list for your half reaction for your cathode, half reaction for your anode, look up the E0 values, standard reduction potentials, subtract one from the other, and you know what your voltage for your cell is going to be. So the Daniel cell, right? We've looked at this one many times. That's the zinc copper cell. Well, we know what the two half reactions are. There's the zinc, and we would write it as a reduction. So it would be zinc 2 plus 2 electrons, goes to zinc solid. That one is undergoing oxidation. That's the anode, right? The copper is the cathode. It's undergoing reduction. We would write the standard reduction potential as Cu2 plus 2 electrons goes to copper solid. We know from the table that the E0 value for the copper half reaction is positive 0.34. How do we know that? We got it out of a table. I'm not going to go all the way back. We got that off the table, and it was measured by building an electrochemical cell where the copper was coupled with the standard hydrogen electrode. Do the same thing for the zinc, which we've already done as well, and we see that its value is negative 0.76 volts. Well, the cathode, positive 0.34, minus the E0 for the anode, minus negative 0.76, is positive 1.10 volts. So this predicts the voltage of this cell, and it's the standard potential. It's got the 0. That means everything's 1 molar, or 1 bar if it's a gas. 1.10 volts. That's what we measured right at the very beginning when we first showed this particular electrochemical cell. So it's true, if you build the cell, and measure it, it'll tell you what the voltage is going to be, but you can predict it as well just by taking those numbers out of the table. So if you needed a cell with a specific voltage, you just mix and match, right? You take the right half reactions with the right values to give you the voltage that you need. How can you tell which one's going to be the cathode and the anode if it's not drawn in this way for you? Well, the spontaneous direction will always have the anode as the one that has the greater E0 value. So we could predict, just looking at these two, well, that one's going to be the anode because its value is bigger. And the cathode is the one that wants to go reduction. It's the one that has a negative value. Sorry, the cathode, I said that the wrong way around. The cathode, the one that wants to be reduced, is the one that has the higher E0 value. The one that wants to be oxidized is the one with the most negative standard electrode potential. So it's always like the big one minus the small one will give you your cell potential for the spontaneous direction of that cell, which makes life a little easy. Let's do this, this one and finish off from here. We have two half reactions. We have lead sulfate plus 2 electrons. That's a solid going to lead solid plus sulfate with a standard electrode potential for that half reaction of 0.36. We have another one, which is lead oxide. So this is the electrochemical reaction that takes place in a car battery. Calculate the overall cell potential E0 cell. Well, E0 cell is E0 cat minus E0 an. It's not telling us what the cathode and anode are. But it doesn't have to tell us. We know in the spontaneous direction, the cathode is going to be the one that's bigger. 1.69 volts minus, the other one is negative 0.36 volts equals, can we do that in our heads? 2.05 volts. Yeah, I think that's right. That's it. Really easy. We didn't have to rearrange anything. Notice that the electrons involved here are the same on both sides. If one of them only had one electron, so then you had to double it so that you could cancel the two half reactions out, it wouldn't affect your calculation here one bit. Doesn't matter. So we talked about how these E0 values are intensive properties. They don't vary depending on the number of electrons that get transferred. So there we go. We get our voltage that way, and you can go look at that list of all the standard reduction potentials, and you can make any voltage that you want. The biggest voltage I guess you could make is around 6 volts with a single. That's if you use the fluorine half reaction on one side and the lithium half reaction on the other side. You could produce a voltage around 6 volts, which is kind of, I guess, an extreme. Probably an easier way to do that would be to use a simpler reaction like this and put several of these cells in series. And that's what happens in a car. Anyone know what the voltage of a car battery is? I don't know the answer to that. I think it's like 18 volts or 20 volts. 20 volts is the voltage of like a cordless drill. So like that would not be done by a single electrochemical cell. That would have multiple electrochemical cells strung together in series to get you to that point. Cool. I'm going to stop here. I think we're good. We got through quite a bit today. We figured out how to calculate the voltage of any electrochemical cell by looking at the two half reactions. I'll be speaking with many of you this afternoon with our oral quiz. If you can talk to the people who already did the oral quiz, they can tell you it's no big ordeal. Hopefully, wasn't too bad. And we'll see everyone on Friday.